A solid concrete slab half a meter thick still allows the deep vibration of a diesel engine to penetrate into a living space. This phenomenon occurs because mass alone follows a logarithmic law of diminishing returns, where doubling the weight of a partition only yields a 6 decibel increase in sound isolation. In structural acoustics, this is known as the mass law, which dictates that the transmission loss of a single-leaf partition is primarily a function of its surface density and the frequency of the sound. For a home builder, relying solely on heavy materials becomes structurally and economically unfeasible when seeking high levels of quiet. Sound energy moves through solid materials as mechanical vibration, traveling at speeds significantly higher than through air. To achieve superior isolation without excessive weight, engineers must look beyond simple density and begin manipulating the mechanical path through which vibration travels. Every rigid material has a specific critical frequency where the speed of its internal bending waves matches the speed of sound waves in the surrounding air. At this precise point, the material becomes acoustically transparent, allowing sound to pass through with minimal resistance. This is the coincidence effect, and it creates a significant dip in the sound transmission class of a wall. For standard half-inch gypsum board, this critical frequency typically falls in the upper mid-range, which is highly audible to the human ear. Engineers mitigate this by either increasing the stiffness of the material to push the coincidence frequency below the audible range or increasing the damping to flatten the resonance peak. Understanding the relationship between bending stiffness and surface mass allows for the selection of materials that do not exhibit these weaknesses in the frequencies most common to residential noise, like speech or mechanical systems.
In standard light frame construction, studs act as mechanical bridges that transmit vibration directly from one side of the wall to the other. When sound waves hit one face of the drywall, the energy is transferred through the screws into the wood or steel stud and immediately out through the opposite face. This direct connection bypasses any insulation inside the wall cavity, rendering the internal airspace largely ineffective for sound isolation. Mechanical bridging explains why a wall with high thermal insulation can still perform poorly in acoustic tests. To break this bridge, the two faces of the wall must be physically separated so they can vibrate independently of one another. This separation is the foundation of decoupling, a strategy that shifts the engineering focus from blocking sound with mass to interrupting the transmission of kinetic energy through the structural skeleton of the building. Staggered stud construction utilizes a wider floor plate than the individual studs to create two independent rows of vertical members. Each row supports only one side of the wall, ensuring that no single stud touches both the interior and exterior wall skins. This design breaks the direct mechanical bridge found in standard framing while maintaining a single wall footprint. While effective at reducing the transmission of high-frequency sounds, staggered stud walls are still limited by their shared top and bottom plates. Since both sets of studs are rigidly attached to the same horizontal members, low-frequency vibrations can still travel through the plates in a phenomenon known as plate flanking. Despite this limitation, staggered studs provide a significant increase in sound transmission class compared to standard framing without requiring the additional square footage of a full double stud wall system.
The most effective method for structural decoupling is the double stud wall, which consists of two entirely separate framing systems separated by an air gap of at least 25 millimeters. By eliminating shared top and bottom plates, the double stud design provides nearly complete mechanical isolation between the two wall faces. This configuration creates a mass-air-mass system where the air in the cavity acts as a soft spring between two heavy masses. The depth of the cavity directly influences the resonant frequency of the system, with larger gaps providing better isolation for low-frequency sounds, like the bass from a home theater or heavy machinery. Filling the cavity with open-cell insulation, like mineral wool, does not block sound directly, but instead provides acoustic damping by converting the movement of air molecules into heat through friction within the fiber matrix. An isolated wall functions as a mechanical oscillator, where the two layers of drywall represent the masses and the air trapped between them represents the spring. The resonant frequency of this system is a critical design parameter because the wall actually loses isolation performance at its own natural frequency. If the resonance occurs at 60 Hz, the wall will vibrate sympathetically with low-frequency noise, potentially performing worse than a single layer of material. To prevent this, engineers maximize the air cavity depth and the mass of the wall leaves to push the resonant frequency as low as possible, ideally below 20 Hz. This keeps the resonant peak outside the range of human hearing and typical building noise. Precise calculation of this frequency is essential for infrastructure near rail lines or airports, where low-frequency energy is the primary acoustic challenge in civil engineering projects.
When space constraints prevent the use of double-stud walls, resilient sound isolation clips offer a high-performance alternative for decoupling. These devices consist of a rubber isolator mounted to the stud, which holds a metal hat channel in place. The drywall is then attached only to the channel, never directly to the studs. The rubber element acts as a shock absorber, significantly reducing the amount of vibrational energy that can pass into the structure. Unlike older technologies such as resilient channels, which are easily short-circuited by long screws hitting the studs, clips are more robust and less prone to installation errors. By creating a floating wall surface, these clips allow for high sound transmission class ratings in high-rise developments and multifamily housing, where floor space is at a premium and structural integrity must be maintained through rigid framing. Damping is the process of extracting energy from a vibrating system to stop it from ringing. In modern wall construction, this is achieved using viscoelastic damping compounds applied between two layers of rigid gypsum board. When sound waves cause the wall to flex, the damping layer is subjected to shear forces. Because the material is viscoelastic, it resists the shear and converts the mechanical energy into a negligible amount of heat. This process is known as constrained layer damping. It effectively reduces the amplitude of the coincidence dip and lowers the overall vibration of the wall leaf. Using a damping compound allows a partition to achieve the acoustic performance of much thicker or heavier materials. This technology is particularly useful for retrofitting existing structures where the framing cannot be altered, but improved sound isolation is required for office privacy or media rooms.
A common mistake in acoustic design is the creation of a triple leaf system, which occurs when a third layer of mass is placed inside a cavity between two existing walls. Physics dictates that two air cavities are worse than one large one. This happens because the air in the smaller cavities is stiffer, which significantly raises the resonant frequency of the wall system. A wall that would have isolated deep bass effectively as a double leaf system often fails to do so when a third layer is added in the middle. The resulting resonance often falls directly in the range of the human voice, leading to a noticeable decrease in privacy between rooms. Successful sound isolation requires maintaining a single, large airspace between two decoupled masses. Avoiding the triple leaf effect is a primary rule for engineers designing high-performance partitions in music studios and luxury residential buildings. Sound isolation is only as strong as its weakest link, a concept known as the flanking path. Even a perfectly decoupled wall will fail if sound can travel around it through shared floor joists, ceiling plenums, or electrical outlets. In civil engineering, flanking through the structure is a major cause of noise complaints in concrete buildings, where the floor slab acts as a continuous transmitter of impact and airborne sound. To prevent flanking, engineers must use acoustic sealants at all joints and ensure that decoupling extends to the entire room envelope, including the ceiling and floor. Small gaps or penetrations for pipes and wires can reduce a wall's performance by as much as 15 decibels. Using heavy putty pads on electrical boxes and flexible connectors for HVAC ducting are necessary steps to ensure the theoretical performance of a decoupled wall is achieved in the field.
The sound transmission class, or STC, is the standard metric used to rate the effectiveness of interior partitions. It is derived by measuring transmission loss across 16 standard frequencies from 125 Hz to 4000 Hz and comparing the results to a standard curve. However, building professionals must be aware that STC does not account for low-frequency noise below 125 Hz, which is common in modern urban environments. For projects near heavy transport or those involving subwoofers, the outdoor-indoor transmission class, or a full octave band analysis, is required. Laboratory tests provide a baseline, but the apparent sound transmission class, measured in the actual building, accounts for the realities of construction quality and flanking. Understanding these metrics allows for the objective evaluation of decoupling technologies and ensures that the finished structure meets the specific acoustic requirements of its occupants. Effective sound isolation in modern civil engineering requires a balanced application of mass, decoupling, damping, and the elimination of flanking paths. We have seen that mass law provides the foundation, but mechanical separation through double studs or resilient clips provides the most significant gains in decibel reduction.
Controlling the resonant frequency of the mass-air-mass system prevents the wall from becoming a radiator for low-frequency noise, while damping compounds mitigate the coincidence effect in the mid-frequencies. Each of these components must be integrated into a sealed system to prevent air leaks from compromising the structure. By applying these physical principles, builders can create environments that remain quiet and functional despite the increasing density of our urban infrastructure. The science of decoupling is not about adding more material, but about intelligently managing the energy that moves through the spaces we inhabit.